Marching right along with our review of everything you know about mechanics, but looking at the angular versions instead. So today we're going to be looking at momentum. The regular linear momentum that we all know and love is P equals mv. This is a conserved vector quantity, and that gives it some interesting properties. You might be able to guess the angular analog. Instead of mass, we're going to have moment of inertia. Instead of velocity, we're going to have angular velocity. And instead of a P, you guessed it, an L. Where that comes from, I have no idea. But this is also a vector quantity, and it is also conserved. So we can say that the initial angular momentum equals the final angular momentum. And this is as long as there are no external torques acting on the system. There can be external forces as long as there are no external torques. So that can take place if the force is acting right on the axis of rotation. Also, angular momentum is conserved completely separately from linear momentum, so you can't convert one to the other. It's not like energy where you just have different types and they're globally conserved. These are independently conserved. Now, one of the important things we had to consider with linear momentum was the direction of the momentum. And the direction is a little bit weird with angular momentum. If you'd like to think about the direction of angular momentum just as clockwise or counterclockwise, so let's imagine we've got some disk here rotating about an axis through the center. If it's rotating clockwise, that could be momentum in one direction, and if it's rotating counterclockwise, that's momentum in the other direction, angular momentum. And if it starts out with angular momentum counterclockwise, it has to end up with angular momentum counterclockwise, and that's completely fine. But they actually define a single direction because this rotational direction is constantly changing. And there's kind of a weird rule here, but it's what's known as a right-hand rule, so it only works if you're using your right hand. But if you take your right hand and you curl your fingers in the direction of the rotation, so in this case, curl them counterclockwise, then your thumb would point in the direction of the momentum arrow. So if you're going counterclockwise, you're going to have an upward momentum, angular momentum vector. And if you are curling counterclockwise, now you have to kind of turn your hand upside down, contort it a bit, so that your fingers are going in a counterclockwise direction, and then your thumb would then be pointing down. And so that's another way that you can describe the direction of the angular momentum. This comes in handy later on with more complex things. We won't get into them in this class, but in advanced physics we will. Alright, on to some examples, because there are a whole host of phenomena that are described by the conservation of angular momentum. Not the least of which is why figure skaters can spin so fast. So if you've seen them do, I don't know what they call these spins, but they'll start out with their arms outstretched, and actually their leg is usually outstretched here too. Here's a leg. And then when they pull all of those limbs in, they have increased their angular velocity by decreasing their angular inertia, their moment of inertia. And essentially I naught omega naught equals I final omega final because of conservation of angular momentum. And so if this guy gets smaller, then that guy has to get bigger. Also, you'll see divers, they'll pull their limbs in to spin faster, and they usually will extend out at some point to slow themselves down for entry into the water. Or if you ever watched those skiers, they used to call it hot dog aerials. I don't know if they still call it that, but they are constantly moving their limbs in and out. Even a snowboarder doing a 1080 or whatever, you'll see them pull their arms in to spin. Anyway, this is going on all over the place. It also is incredibly important in astronomy. One thing that can happen to a star as it dies is there's no more fusion in the center, causing pressure to go out, so the star can collapse on itself. And it can create what is known as a neutron star. And a neutron star is about the size of a city, but you take the mass of an entire star and cram it into that size. So it's very dense, but it also follows this same conservation of angular momentum, and that can cause them to spin really quickly. So if we do a quick little calculation here where we say initial angular momentum equals final angular momentum, and we're going to apply this to our star. The moment of inertia for a spinning sphere is, I think it's 2/5, yes. So 2/5 times the initial mass times the initial radius squared, all of that is our moment of inertia, times the initial angular velocity squared. And then we've got that same factor because the neutron star is still a sphere, times the final radius squared. And that is going to equal our final angular velocity. Oh, not squared. Get rid of that. Now this goes away, the factor of 2/5, and we are assuming no loss of mass. Now a real star will probably lose some mass, but it will keep a whole lot of it. But for simplicity, we will say that the initial mass equals the final mass, so we can cancel those guys out. And we want to find the final angular velocity, so we can just solve for it like this, divide that final radius to the other side and just square the whole thing. And there we're in business, so we can plug in our numbers here. We're given the initial radius is 7 times 10 to the 5th kilometers. And because we have a ratio here, this is in kilometers, and the final radius is also 10 kilometers. So those units are going to cancel out, and you don't need to worry about converting to meters. So that is squared. Now, we're not given our initial angular velocity in terms of radians per second. We're told that it spins around once every 10 days. So we can find that by doing 2 pi times the frequency. So the frequency is 1 revolution in 10 days, and then we can just multiply by 24 and by 3600 to get that to seconds. This thing works out to be 7.272 times 10 to the negative 6th. So if we plug that in here for our initial angular velocity, 7.272 times 10 to the negative 6th, and throw all this stuff in there, and we will get 35,633.8 radians per second. And if we multiply or divide by 2 pi to get it back to frequency, so omega over 2 pi is going to give us 5,671, there's my one, erase, okay, 71 revolutions per second. So this guy is cooking along over 1,000 times, almost 6,000 times every second. And they do find neutron stars that are spinning this quickly, so pretty incredible thing. And this has this idea of conservation of angular momentum, as I mentioned earlier, has lots of applications in astronomy. This is how we think stars and star systems, solar systems around stars form to begin with. Is you have this large nebula, this cloud of gas and dust, and it slowly collapses on itself due to gravity. And as it does that, it starts rotating, because if it was moving even a tiny bit when it was really large, by the time it collapses down, it's going to be rotating. And that's why everything in the solar system, for the most part, is rotating in the same direction. It all came from the angular momentum that the nebula had to begin with, and that was conserved. So there is that. Something else to look at, if we're looking a little more closely at this vector nature of angular momentum, right? We said L equals I omega. So if you have a person standing on a giant disk, I don't know where this giant disk came from, but anyway, if they're initially at rest, then the angular momentum is 0, and if they start walking in this direction, they are considered to have angular momentum because they are going in a circle. And so their angular momentum would be up. But we need to, just like with linear momentum, if we create momentum where there was none to begin with, we need to have momentum in the other direction to cancel it out. So what's going to happen here is the disk is going to start rotating in the other way. And if you point your fingers, curl them in that direction, then your thumb will be pointing down. And so the angular momentum of the platform will cancel out the angular momentum of the person, so that we can conserve angular momentum. And where better to see this than on The Simpsons? So enjoy a little clip here.
Run, Ralph, run! Time to do what I've never done as principal. Something.
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is so cool! That's the kind of stuff they should teach in school!
We do teach it in school. You're too busy eating sugar snacks and horsing around.
He's right. Learning can teach you things. Education rules.
Alright, getting back to the real world here. We have one more example we're going to look at. If you have a person standing on a turntable and they're holding a wheel that happens to be spinning, yes, we physicists like contrived situations. And I'm actually going to show you this in class though, so this is going to happen. And I'm not going to tell you the answer. I want you to think about what's going to happen if this wheel is spinning in this direction and it's got some angular momentum in the upward direction, and then you flip the wheel. What is going to happen? Dun dun dun. You'll have to wait and see in class.